Okay, during the break, I'm going to do a quick recap. I forgot to record the first hour of lecture, so let me do a quick recap. And so I'm going to just start from here and go backwards. We're talking about skeleton redox, and skeleton redox had different conditions can result in different products. And so when we look at ethanol, the oxidation of ethanol, it could occur very violently, like in a rocket engine. Let me just show you that. And so I'm going to try to compress 1 hour's worth into a short time here. But for this is for those who are absent and who are watching the recording. Here, I don't want to get rid of these drawings yet, but let's take a look. This is combustion of ethanol with liquid oxygen. This is a 12 kilonewton, which is force, rocket engine. 12 kilonewtons is pretty huge force. This is burning insulation here. This is starting to glow. This, I think, is ceramic, starting to glow white hot. Let's fast forward. Let's fast forward it. All right. So here we saw that the ethanol can burn quite violently, like that. But this is with oxygen, but it could also not burn so violently, like in the body. In the body, when ethanol is consumed in the body, it takes time and undergoes numerous steps in being oxidized by the body. And so let's say you had an alcoholic beverage, and you aren't going to get a flame like that, even though, essentially the same reactions occurring in the body, but it's happening in different steps. And so when you have ethanol, say you drink some ethanol and then you inhale oxygen, eventually this is going to be oxidized to CO2 gas, which you're going to exhale plus energy. It's not going to happen in one huge explosion or flame like this. It happens in multiple steps. So in the body, it gets partially oxidized to maybe like ethanol, which is an aldehyde, or eventually to something like acetic acid, which is essentially vinegar. And so it'll undergo steps in its way to being oxidized. So what we have is we have something called partial oxidation. This will be complete oxidation to CO2 and water. Now, how do we get partial oxidation with oxygen? Oxygen is a powerful oxidizer. The way we get partial oxidation is we alter the conditions. Certain things change the conditions, like concentration. Here they're using highly concentrated oxygen, which is liquid oxygen. There's very little empty space. And then they're force feeding it into this rocket engine. Here, the conditions change. And so we have partial oxidation. So we can use a powerful oxidizer like oxygen, but under conditions of low concentration or low pressure. We could also use more milder oxidizers, and there are milder oxidizers present. And so this is part of the pathway in the metabolism of acetic acid. And there are different oxidizers that are used, milder oxidizers or different conditions that they're used under in undergoing this. And so this partial oxidation, this type of stuff is difficult to predict theoretically, and so I was talking about over here. Let's go back to this. This will be my 15-minute recap since I'm just on break. We'll go back over here and we'll look at hydrocarbons. When we combust hydrocarbons, hydrocarbons are compounds containing carbon and hydrogen, or compounds that contain carbon, hydrogen, and oxygen, CXHYOZ. That's what it's supposed to be. These constitute the alcohols, the ethers, the sugars, etc. Like, for example, ethanol. When we burn ethanol, you know, in a flame with oxygen, we might get carbon particles, which are soot, and this creates a black gray smoke, soot particles, or we might get carbon monoxide, you know, from incomplete combustion or partial oxidation, or we might get CO2, complete combustion. And so, you know, under what conditions are we going to get these? Well, that rocket engine is only going to produce CO2 and H2O, you know, but under other conditions, we might get carbon monoxide. Well, that happens all the time in methane. You know, a lot of people end up dying from carbon monoxide poisoning from their stoves, their furnaces, their water heaters, you know, not combusting completely. You know, there's not enough oxygen getting in there. The ratio of fuel to air is all out of whack. And so carbon monoxide is a dangerous product. Well, on the other hand, let's say we want to study carbon monoxide. Let's say we want to make all carbon monoxide. And so under what conditions can we burn this to get all carbon monoxide? Well, that's very difficult to predict theoretically. And so what chemistry is a mix. You know, chemistry is a mix of theory. Theory is great because we could use theory to predict things. And that way we don't have to memorize it. If we could just use theory, then there's no need to memorize anything. However, the theories is very complex, the mathematics of the theory. We're going to talk about theory in the next chapter. And so the theory is too difficult to do. So in chemistry, we have to do a mix of factual observations and theory. And so in terms of factual observations, we just try varying the conditions. You know, the conditions, you know, change. You know, what products are formed. So we might try to increase the level of oxygen, you know, not all the way to liquid, but, you know, higher and higher concentrations or lower and lower concentrations, which brings me to skeleton redox. The methodology in skeleton redox is just experimental observation. Just mix it and see what happens. You know, this is not a theoretical prediction. We're just going to try it experimentally and see. And so this brings me to a story of when I was camping in Joshua Tree. Let's see, when I was camping in Joshua Tree, I had a bottle of wine and that I bought at the dollar store, you know, Santa Barbara wine. So I couldn't pass it up. But the reason they had it at the dollar store was because the wine had turned into vinegar. Because when I brought it back to the campsite, it was a very expensive bottle of vinegar, $1. I wouldn't have paid that much for it. And so what happened was the ethanol in the wine must have been partially oxidized to vinegar here. That's what happened. I would have liked it had the ethanol been completely oxidized to CO2. If the ethanol in the wine had been completely oxidized to CO2, then I would have sparkling grape juice. But unfortunately, it wasn't. The ethanol was only partially oxidized because what must have happened was a little bit of oxygen must have leaked through. And that little bit of oxygen resulted in partial oxidation. And so we use skeleton redox to figure what's going on here. So the first step in skeleton redox here is to figure out, you know, what happened to the ethanol. And so we use the steps in skeleton redox here to come up with a balanced half reaction. This is what we call half reaction. Ethanol and water is going to be the reducing agent here, and acetic acid and H+ will be the oxidizing agent if we went backwards, because that's gaining the electrons. And so we could see that using oxidation states. Now the oxidation states I did using structure. You know, the average here is -2 on the carbons. The average oxidation state here is 0. We did that structurally. I'm going to do the structure more in the future. So I'm cutting out a lot. You know, we also looked at ammonium nitrate. You know, it's the worst industrial accident that happened in the US was from ammonium nitrate. That was in Texas City. I'll post the link there. And then the oxidation states we're going to look at in detail once we get to the Lewis structure chapter, where we'll see that this carbon's a -3, this carbon is -1, and the average is -2. And this carbon's a -3, and this carbon was a +3. And so -3 and +3, the average is 0. And so that was based on that. Okay, but unfortunately, I'll have to cut that out with this recording. So we'll see it again. So that was some of the key topics I covered in the past hour, but forgot to record. Okay. Hopefully I'll record it next time. It is break time. We're on break. We're going to resume break. This was just a brief 15-minute synopsis of the last hour breaks, since I forgot to do the recording. Okay, so I'm going to pause the recording now. Okay, so when you oxidize ethanol in your body, you could produce vinegar or acetic acid. Also in the flame here, there could be acetic acid, those types of things. But in the body, we aren't going to produce carbon monoxide. These types of things don't happen because it's under different conditions. The types of conditions you use, even though oxygen is the same, oxygen is ultimately the oxidizer, the conditions have totally changed the products, here. And so it's quite a bit different. So conditions are so important. So this is why skeleton redox is important, because yeah, who knows what we're going to predict. So the easiest thing is just to try it and see what happens. And so here we have what's happening with the ethanol, and then keep that in mind here. Now, what's going on with the oxygen? What's going on with the oxygen, we can just get off the redox chart. And so let's just copy it off the redox chart here. So let's take a look at the redox chart. Actually, I need to go back to that. And so when we look at the oxygen here, we want to pick the stronger oxidizer here, and blow this up. Fortunately, I don't want to erase these, otherwise I'll have to rewrite everything. But here we have it. Oxygen is a pretty moderately strong oxidizer, and we have O2 plus 4H plus 4 electrons yields 2 water. So we're going to use that, because oxygen occurs on the chart. Ethanol does not occur on the chart. And even if ethanol occurred on the chart, there are multiple products that we might have. So if ethanol occurred on the chart, we don't have enough room to write all the possible products. So we just assume if ethanol reacts, we always assume it reacts to completion, to complete oxidation, which would be CO2. CO2 would be the final ultimate end product. We already said things like CO3 don't exist. And so let's take a look. Go back here. So let me go with black background here. What's going to happen with the O2 is we just copied off the chart. And so the O2 is going to be like this. We'll have O2 plus 4H plus 4 electrons yields 2 H2Os from the chart. And so one of these is from skeleton, from experimental observation. Experimental observation was I tasted the wine, and the wine tasted like vinegar. And so from experimental observation and skeleton. This is from the chart, oops. And so what I'm going to do is I'm going to combine these two and see what happened to my wine. When I combine these two, I'll add everything up on the left. So I have my ethanol, CH3, CH2OH, plus water. 4 electrons cancel, so I don't have to multiply anything out. So plus a water, plus an O2, plus 4H plus 4 electrons. So that's everything on the left, plus everything on the right. And so on the right, I'm going to have my acetic acid, CH3COOH, plus 4H plus 4 electrons. And then over here, plus 2 H2Os, plus 2 H2Os. And now what I'm going to do is I'm going to simplify this. And so let's work on simplifying this. I see I have one water here, so let's cancel out that water, and then 2 waters here, so I'll cancel out one of the 2 waters here. I got 4 H pluses on both sides, I'll cancel that out. 4 electrons on both sides, I'll cancel that out. And so the overall net reaction that I see is I'm going to have CH3, CH2, OH plus O2 yields CH3, COOH plus H2O, O2. So the ethanol that was in the wine, so it's aqueous ethanol, was oxidized by a little bit of oxygen that got through the cork, you know, in the bottom. Like I said before, the cork wasn't providing a good enough seal, so a little tiny bit of oxygen leaked in and partially oxidized my ethanol, partially oxidized it to acetic acid, vinegar, which is aqueous, and water, H2O liquid. And so this is the balanced redox reaction here that occurred. There's a driving force here. There's a driving force because I did taste the vinegar, so something had to happen. And so here, the ethanol is our reducing agent. This is our reducing agent here. And we have a conjugate. This is a conjugate agent. This would be our oxidizing agent here, the oxygen. This would be our conjugate reducing agent here. And so the ethanol here is our reducing agent. The oxidizing agent is oxygen, and then it goes to acetic acid. Acetic acid would be our conjugate oxidizing agent, and water would be our conjugate reducing agent. And so what we can easily see the driving force here. We don't need a chart for the driving force because ethanol versus water, which is easier to burn? Remember, reducing agents are fuels. And so which fuel is easier to burn, ethanol or water? You could build a fire using ethanol. Could you build a fire using water? No. And so that means ethanol's got to be stronger, water's got to be weaker. And likewise, what's a better oxidizer, oxygen or acetic acid? You know? And so let's say you're trying to make the flame bigger. Should you blow air on it to get more oxygen to the flame, or should you pour vinegar on it? Which one do you think is a better oxidizer? Well, oxygen's a better oxidizer. It's going to be stronger. Acetic acid is going to be weaker. And so there's the driving force there. We know there has to be a driving force because in skeleton comes from observation. And if you observed it, therefore, there must be a driving force. Otherwise, you wouldn't observe it. If there's no experimental observation, then there's no driving force. In that sense, in the sense for skeleton. And so that's what we have here. And so this is the utility. Sometimes, you know, both the reducer, ethanol, and the oxidizer doesn't occur on the chart. And if we have a scenario like that, or the oxidizer might occur on the chart, but it gives a different product, you know, that's another scenario that we might have to do skeleton for both. In this case, we did skeleton for the reducer, but we didn't have to do skeleton for the oxidizer in this case. And in the case for what the explosion that happened in lab, I don't know if did I talk about the explosion that happened in lab before the break? Yeah. Yeah. The explosion that happened, this was the Chem 1B lab, so Chem 1B students should know better, but you can't always assume that. So let me clear the drawing. Unfortunately, the oxidizer doesn't have to be oxygen. There are plenty of oxidizers around. And so I had an explosion without oxygen even participating in it, and didn't have to participate, let's say. But basically it was ethanol, like this, and nitric acid, HNO3. And nitrate is a powerful oxidizer here. We know that. And so this resulted in an explosion. If it's an explosion, then the ethanol, I would assume it was completely combusted. You know, it's an explosion. And then the nitrate we know, you know, when nitrate acts as an oxidizer, right? Nitrate's a good oxidizer. This is what happened to the Grand Camp. The nitrate oxidized ammonium nitrate. Ammonium nitrate resulted in the worst industrial accident in the US. The nitrate oxidized the ammonium, and that resulted in the complete destruction of 2 huge ships. The Grand Camp and the Flyer. What was the other name? I forgot. But nitrate, we know nitrate's a good oxidizer. Nitrate plus 4H plus 3 electrons. This is reading it off the chart, yields NO gas. NO gas, remember, is nitric oxide or nitrogen monoxide. Nitric oxide is colorless, but this is rapidly oxidized, you know, in air. So NO gas plus 1/2 O2. Sorry if I'm repetitive here. I'm just doing this since I screwed up and didn't record the video. There's a lot of things. That was an important video to record because there's a lot of things not in the book in the first hour. And so NO2, this is the beautiful red-orange smoke that they saw. This is a red-orange gas. It's the smog, photochemical smog, the brown smoke there in LA. So anyway, NO, these are all pollutions, but NO, again, has inorganic properties, pollution, but it won a molecule of the year because of its biological properties. So even though NO is photochemical smog, it does have important biological properties, especially in terms of blood and circulation. So the NO gas plus 2 H2Os, liquids. So this is from the chart. And so what we have to do is we have to get the ethanol from skeleton. And so this resulted in an explosion. If it was an explosion, this happened in lab. So fortunately, shooting the students, they were not badly injured. So the ethanol, we got to assume it reacted completely. If ethanol reacts completely, what does it form? You know, not partially, completely. And so when ethanol reacts completely, like we'd have an explosion or in the rocket engine, you know, that rocket engine, you can't get more complete reaction of ethanol than that, right? So if ethanol reacts completely, what forms? Yeah, CO2. So we're just going to look at the H2O. We don't have to worry about in skeleton because H2Os we'll figure out later. H pluses we'll figure out later. So hydrogen and oxygen we don't worry about. And so here, this is different. In the previous example, I did partial oxidation. Remember, my wine was partially oxidized, you know, and partial oxidation depends on conditions. You know, for example, like I said earlier, you could use a strong oxidizer like oxygen, but just under very dilute, you know, tiny bit leaks through the cork in a wine bottle. Or you could use mild oxidizers. You know, there's lots of mild oxidizers around, not really powerful. Nitrate is a powerful oxidizer, but it could be mild if you dilute it way down. So like if you had concentrated nitrate in H+, like nitric acid, that's a different story than something that's very dilute, you know, like if you didn't have very much nitrate in there, then it could be mild. So, you know, even with something like nitric acid, you know, we could have mild conditions if the nitric acid is very dilute. But unfortunately, during that lab accident, you know, the student accidentally poured the ethanol into a concentrated nitric waste jug. And so that was the disastrous part there. That's why it exploded. But going back to this, we do the same thing here, but in this case, we have 2 carbons, so we balance all elements other than hydrogen and oxygen. Over here, we only have 1 carbon. And so Kazra, this is the case where it's okay to change the coefficient here to 2, because it's not going to mess up anything. Yeah, it changes the oxygen, but we haven't gotten there yet. And so now we have 2 carbons. You can only do this in the first step, otherwise it messes everything else after that up. And so here we can add a 2 in front. And then we balance out the oxygens. And so we have 1 oxygen over here, and then 4 oxygens here. And so again, we balance by adding water. So we're going to add 3 waters over here, like that. And then we balance the hydrogens. So we sum up all the hydrogens. 3 plus 2 plus 1 is 6, plus 6 is 12 hydrogens on the left. And then over here I have 0 hydrogens on the right, so I need to add 12H plus. And then we balance out the charge, making sure that the charge on both sides is balanced, whether it's 0 or not. On the left, it just happens to be 0. Ethanol is neutral, water is neutral. On the right, CO2 is neutral, but hydrogen is plus. And we got 12 of them, so it's plus 12. And so this is plus 12 electrons. You can see ethanol is pretty electron rich. It's losing 12 electrons, according to this. Now, we're going to have CH3, CH2OH, plus 3 waters. It's our reducing agent. This is going to go to 2 CO2s, plus 12H plus, plus 12 electrons. So in the explosion in lab, the ethanol was not partially oxidized. The ethanol is fully oxidized, CO2. And this would be our reducing agent again. Ethanol is our reducing agent. And then this would be the conjugate oxidizing agent here, CO2 and H plus. The reducing agent would be here. So this is one of the half reactions. The other half reaction we just get from the chart, which is nitrate and 4H plus, this one. And then we combine them. When we combine them, we have to multiply the first one by 4, because we only have 3 electrons here. We need 12 electrons. So we'll multiply the first one by 4, and I mean this top one by 4, and this bottom one by 1, and then add up everything on both sides. And so if I add up everything, I'm going to have ethanol, 3, so this is supposed to be it's 2, CH3, CH2, OH. Go with a finer pen, that's probably what I need. CH3, CH2OH plus 3H2O plus nitrate. And now I have to multiply it by 4, so I'm going to need 4 nitrates here. Plus 4 nitrates, and then 4 times 4 is 16 H plus. Plus 4 times 3 is 12 electrons. So that gives me 12 electrons. So that's everything on the left. And then we combine everything on the right. So everything on the right would be 2 CO2. Those are gases. I'll put in the states later. Plus 12 H plus. Plus 12 electrons. Okay, now here I have to multiply everything. 4 NOs plus 4 NOs plus 4 times 2 is 8 H2O. All right, now what we're going to do is we're going to simplify this, getting rid of spectators, or they aren't really spectators, getting rid of things that occur on both sides. So I have 3 waters here. Let's cancel 3 out of the 8. That leaves me with 5. And then what else? I have 12 H pluses here as a product and 16 here. So let's get rid of 12 out of the 16. That's going to leave me with 4. And then the 12 electrons here, cancel the 12 electrons here. That's it. Okay, now when we combine it, then we're going to get the ethanol. Plus nitrate. Plus 4H plus. 4 nitrates plus 4H plus yields 2 CO2s plus 4 NOs plus 5 H2O. All right, putting in the states here, ethanol is, in this case, ethanol was a liquid. It was pure ethanol, I think, that she was dumping in there. Nitrate's going to be aqueous. Or aqueous for this, there's water around. H plus is aqueous, CO2 is a gas, NO is a gas, H2O is a liquid. So these are the states. Now we look, ethanol is a reducing agent. Nitrate and H plus, this is our oxidizing agent. We need the H plus with the nitrate because we're forming water. CO2 is our conjugate oxidizing agent, and NO and H2O, this is our reducing agent. I can see that from up here. Ethanol and water. Oops, I can see that from over here. Ethanol and water, that's a reducing agent. That's conjugate oxidizer, which is CO2 and H plus. H plus is missing here. And then the oxidizer here is nitrate and H plus. And its conjugate reducer would be NO and water. This would be conjugate reducer. And so that's where I got the labels. Now again, this was observed, you know, and so this is from the explosion. And so this was observed, an observation that the ethanol must have been completely reacted to CO2. This is from the chart. And since it was observed, there was a driving force. So this has got to be stronger, stronger to weaker, weaker. But we could easily see that because what's a more powerful oxidizer? Nitrate and nitric acid or carbon dioxide? Carbon dioxide is a very, very weak oxidizer. The only thing that carbon dioxide could oxidize are things like magnesium metal, you know, like we saw in the video, YouTube, or other metals. CO2 can oxidize metals that lose their electron easily, but not ones that don't, like gold, platinum, copper. CO2 wouldn't be able to oxidize those. Just the metals that, like lithium, that can easily lose electrons. And so this is going to be a much stronger oxidizer than this. Nitric acid will eat up lots of metals, including copper metal. You know, ethanol, what's easier to burn, ethanol or nitrogen monoxide or nitric oxide? You probably don't know that so well, but ethanol is electron rich. NO is +2 on nitrogen, so it's poor. So this is stronger to weaker. And so this would be the driving force we have. And so this was the explosion that I had in the lab. So, and this is a different oxidizer. You know, we don't have to have oxygen to catch ethanol on fire. We could use other oxidizers as well. Okay. All right, so that's an example of skeleton. Skeleton, what you're going to be given is you're going to be given the reactant and products, but it's just not complete. Now, how do you know it's complete? Well, we got to balance this. We just did. We got to double check that it's balanced. We can double check the half reactions here if they're balanced. We double check it by doing atom balance and charge balance. Well, we just did that, but let's make sure we didn't screw it up at the end. It's easy to screw it up, you know, by misadding these. But anyway, we have 2 carbons here, 2 carbons here, 3, 5, 6 plus 6 is 12 hydrogens, 12 hydrogens. 1 plus 3 is 4 oxygens, 4 oxygens. So the atoms are balanced. Then we check the charge, 0 and 0. 0 plus 12 minus 12, which gives me 0, so it's balanced. We could check it here too. 1 nitrogen, 1 nitrogen. 3 oxygens, 1 plus 2 is 3 oxygens. 4 hydrogens, 4 hydrogens. So the atoms are balanced. Then we check the charge. -1 for nitrate, -3 for the electrons gives us -4, +4 is 0. This is 0 and 0, 0 and 0 works. And then we could check the balance of the final equation. There should be no free electrons here, but we got to check the atom and charge balance. So there's 2 carbons. Oh, there's 2 carbons. I have 2 carbons here. There's 3, 5, 6 hydrogens, plus 4 is 10 hydrogens on the left. 5 times 2 is 10 hydrogens on the right. Then I look at the nitrogens, 4 nitrogens, 4 nitrogens. So the atoms are balanced. Then let's look at the charge. Is 0 minus 4 plus 4 is 0. This is 0, 0, 0, it's 0. So this is balanced. We double checked it, the charge and atom balance. And then we have it right. And so the skeleton is, again, you know, we have some additional observed products for this reaction. So I got the skeleton. Okay, there are skeleton reactions in your book. So let's look at one more example of a skeleton reaction. Okay. from the book. Get rid of this. Okay, got logged out. Oh, unfortunately, the video, the resolution on the video, the YouTube video I showed you, was poor. This video, there's a much higher resolution version out there. The black and white footage is clear. That black and white footage was very difficult to see. But this is the Texas City explosion here, so sorry about that. This one was fine. Let's see what else we got here. Okay, Krakalichi. Now I'm deviating quite a lot from the book's presentation. And so, let's see what chapter was skeleton redox. Another chapter. Since I'm deviating from the books, it's a mix of things, chapter 8 and 9 plus chapter 19, but the reason with chapter 19, things get a little bit complicated because chapter 19 has a lot of battery stuff in there. And so here they're going through figuring out the skeleton redox. So we have nitrate going to nitric oxide, but we already know that. We don't need this one. Nitric going to nitric oxide is on the chart. This was a nitrate, as you call it. It's nitrate plus 4H plus 3 electrons yields NO and 2H2O. We could have gotten that from the chart. And so this one was kind of pointless because we could have gotten it from the chart. We want things that aren't on the chart. And so in this example of skeleton redox, what they did was they reacted iodide with sulfate and they got some kind of reaction that occurs. And when they looked at the products, they saw that some iodine formed, which is purple solid, plus some sulfur formed, which is a yellow solid. So they observed this. This was observed in this particular one. And so this one is a more useful example than the last one here. Although iodide's on the chart. If we look at iodide, we can just copy it off the chart. 2 iodides goes to an iodine plus 2 electrons. And so it's written on the chart as iodine plus 2 electrons yields 2 iodides. And so it's off the chart. We just reverse it, you know. And so this is from the chart. We reverse it and then we'll have it iodide going to iodine. So that one we copied off the chart. The other one we don't have on the chart, because if I look at sulfate, this is sulfate going to sulfur, elemental sulfur. This one is not on the chart. Let's go back to the chart and I'll show you what I'm talking about here. So when I go back to the chart here and I look at sulfate, I have sulfate here, but when sulfate's acting as the oxidizer in this particular reaction here, The sulfate is not going to elemental sulfur. The sulfate is going to sulfur dioxide. And so this is slightly, well, under different conditions, we'll form different products. As you recall, when we burn hydrocarbons or carbon, hydrogen, oxygen containing compounds, we could form soot, you know, elemental carbon. Well, in this case, we don't have to burn it, you know, completely, although SO2 is not totally complete, as this is +4. Sulfur can go to +6. But sulfur dioxide is a very common product. We can just do partial, you know, oxidation to just this elemental sulfur instead. And so it's under different conditions. So this sulfate we can't get off the chart because it's a different half reaction on the chart, sulfate going to sulfur dioxide. And so what we have to do is we have to figure it out. And so figuring out the steps here, the sulfur is already balanced. Then we balance the oxygen. So we need 4 waters on this side. Then we balance the hydrogens. We need 8 H pluses on this side. And then we balance the charge. You know, so here they're talking about oxidation states. You know, sulfur is going from +6 to 0 here. And going from +6 to 0 means it's gaining 6 electrons. And so iodide's already done. So here sulfate goes to sulfur. So we need to balance out the oxygens, 4 waters. Then we need to balance out the hydrogens, 8 H pluses. Then we need to balance out the charge, you know, +8 minus 2 is +6. +6, we need 6 electrons. And then we have the balanced half reaction here. And then we combine the two. So now we combine the 2 half reactions, making sure the electrons cancel, you know, 6 electrons gains, 6 electrons lost. Electrons have to cancel. And then we double check, are the atoms balanced? Are the charges balanced? So here they're balancing the atoms, next they're balancing out the charge. So this is another example of skeleton, but you know, half this skeleton is off the chart. Let's look at some other examples of skeletons that might not all be on the chart. And so what section is that? Writing redox 19-8. So when I look at this, I have these to deal with. So thiosulfate going to sulfate, this is not on the chart, so we have to do this skeleton. However, chlorine going to chloride, that's on the chart. Just copy it off the chart. Zinc going to Zn2+, that's on the chart. However, antimony, this is diantimony pentoxide, going to this antimonite ion, this would be O+. This one is skeleton. These are for the half reactions. All right, tin going to this, well, that would be stannite. So this would be stannous acid. Would be skeleton. And then nitrate going to nitrogen dioxide. This has got to be skeleton too, because on our chart, we have nitrate going to nitrogen monoxide or nitric oxide. That's on our chart. And so this is a case where we have both skeletons. So what you do is you split it up. The tin goes into H2SNO3, and then the nitrate goes to NO2. And so we balance this one out, we balance this one out, and then we combine the 2 halves once we're done. Combine those. All right, nickel 2 going to nickel 4 oxide. This is going to be skeleton. But tin 2 going to tin, that's going to be right off the chart. This is oxalate. Oxalate going to CO2. Oxalate, you can combust to CO2. Oxalate going to CO2, this has got to be skeleton. But permanganate going to manganese 2, that's right on the chart. You know, if we go look at the chart, we just write it, copy it straight off the chart. It's permanganate plus 8H plus this is manganese 7 going to manganese 2 plus 5 electrons. I figured out how many electrons because this is manganese plus 7. The oxidation state, this is manganese plus 2, so go from +7 to +2, we need 5 electrons for each manganese. We only have 1 here, so That's it. This is going to go to manganese 2+, and then I figured out how many hydrogens I need because how many oxygens. I have 4 oxygens, therefore I need 8 hydrogens to make 4 H2Os. Good. That's it. Or just read it. I just copy it off the chart. We copy it off the chart, which is fine. We get the exact same. Here. Permanganate. Oh, this is the wrong one. This is going to MnO2. Oh, shoot. They changed, they screwed up this chart. I'm sorry, I used the wrong one for this one. I don't know why they did that. The copper is screwed up on this chart. I have to go to the previous edition chart to look at it. Maybe our book has it. Let's look at our books chart. And so when we look at our books chart, do they have permanganate? Our books chart does not have permanganate here. And so the chart you should get familiar with is not the one I put on, unfortunately, on the slide. The chart you should use is on Piazza. Here. This one. Permanganate's a top 5 oxidizer here. It's a very powerful oxidizer. Manganese is in +7. Plus 80 pluses plus 5 electrons yields Mn2+ plus 4 waters. This is the one you should use. I don't know what happened with that chart. They screwed it up. Here we have copper and copper 2. That's the one we need, not copper and copper 1. Okay, let's go back to what we're looking at. So this is on Piazza, this chart. What did I do with that? Okay, here we are. So permanganate to manganese 2 is right off the chart. I'm just copying it right off the chart there. But oxalate to CO2, we're going to have to do that using skeleton. You know, the standard procedure. Let's see what they did here. No. Oxalate to CO2 is not that hard to do using the standard procedure. Let's go on here. Both of these are, oh, actually, no, chloride to chlorate is not on the chart. And so chloride to chlorate, we're going to have to use skeleton for that. And so chloride goes to chlorate, we do skeleton. And then nitrate to NO is right off the chart. That one's common. Dichromate to chromium 3 oxide, that's not on the chart. We have dichromate on the chart, but dichromate doesn't go to chromium 3 oxide. On the chart, dichromate goes to chromium 3+ ion. And then we have ammonium going to nitrogen. So both of these we have to do separate. So we break it up into 2 separate. We'll have the dichromate goes to chromium 3 oxide. And then we have the ammonium goes to nitrogen gas. And so we have to balance each of these individually using the techniques there. Sulfate goes to SO2, that's going to be skeleton, and then mercury goes to mercury 2+. That's going to be skeleton, I think. So both of those. Here we have arsenic 3 oxide goes to arsenate. That's going to be skeleton. But nitrate goes to NO, that's chart. So we can copy that off the chart, but arsenic 3 oxide goes to arsenate. We are going to have to do that using the skeleton procedure. PB2+ goes to PbO2. That is on the chart, I think, on my chart. Let me check. PB2+ goes to PbO2. So we have PbO2. That's on the chart here. So we could just copy it. We have to reverse it. So this would just be reverse because Pb2+ is the reactant. So the first reaction is we just take Pb2+ plus 2H2O liquid goes to, that's Pb2+ plus 2H2O liquid goes to PbO2, which is product, plus 4H plus 2 electrons. So this one we can copy off the chart. Pb2+ goes to PbO2 is on the chart. What about the other one? So let's take a look at the other one. Zn2+ goes to Zn is on the chart. Both of these are on the chart. We don't need skeleton redox. The reason it's in the skeleton redox section here is because your book, it's not in the Chem 4 chart. So, but it's in the chart I gave you, so there's no reason. And so we can copy both of these off the chart and then just add them up, making sure the electrons cancel. That's it. And so, could do that. Let's take a look. Next page. All right, that was all of them there. Unless there's something in the advanced. Let me look if there's anything in the advanced. This is electrolysis of sodium chloride. Electrolysis of sodium chloride can make elemental sodium and elemental chlorine, sodium metal and chlorine gas. Talking about batteries, electrochemistry. All right. So this is some examples of skeleton redox. Now what we're going to do is, actually, let me talk a little bit more about redox. So I'll talk more about redox. MedCram is a site subscribed to. Has a lot of useful information, especially about COVID. All their this is a paid site because they have some instructional videos for medical students and practicing physicians. But all their COVID videos are free, and so they have a whole bunch of things on COVID-19. One of the issues with COVID-19 is the issue of blood clots, thrombosis. This is different than the flu. In the flu, people don't get blood clots. And these blood clots lead to all kinds of problems. Like if you have blood clots in the lungs, or blood clot in the heart, or blood clot in the kidney, or blood clot in the brains, that leads to different symptoms. And there are a wide variety of symptoms for COVID-19. And so what's causing blood clotting in COVID-19? And so one of the things that, or there are actually two hypotheses for what's causing blood clotting in COVID-19. One hypothesis is that the coronavirus plays a role in linking, platelets together and causing this kind of aggregates to form, so the coronavirus can link these, it's bond to one and bond to another, and then we get this kind of clumping. Another hypothesis is that the coronavirus attaches to the ACE2 receptor in endothelial cells. Endothelial cells line, your veins, vessels, and it causes damage. And when your blood vessels or blood veins or whatever get damaged, then the body's natural tendency is to start a cascade of processes that result in clotting of blood, because of let's say your blood vessel's damaged and you're bleeding, you don't want to bleed to death, and so the body's natural response is to clot the blood to plug up any gaps or holes in the blood. And so let's take a look at that hypothesis here. Let me see, is this one it? I should have checked this a little earlier, but this is the hypothesis that he made here. Let's take a look regarding this. Turn up the volume.
Needs to be given to have an adequate immune response without having too many side effects.
Oh, this is talking about the book.
Here is.
Let me find it. Okay, this is one of the, this is the first hypothesis. In fact, both might be at play or neither. These are hypotheses. So hypotheses need to be tested to make sure that's what's happening. But there's lots of observations that lead them to this particular hypothesis. And so this is one of the hypotheses about blood clotting here. And this is the CD147.
Now for that, I want to jump down here to the third paragraph. They say here, the proposed catch and clump scenario for COVID-19 has a parallel in malaria. As we just talked about, CD147 is central to the infectious process of malaria into the red blood cell. But what is it that's happening in COVID-19? Well, for that, let's go to the second paragraph. And they say here, the potential for major dose response gains is evaluated based on studies indicating that ivermectin shields SARS-CoV-2 spike protein, and that this spike protein is supposed to be able to bind to CD147, but ivermectin prevents this from happening. It also potentially prevents it from binding to the ACE2 receptor. Now,
I actually skipped a bunch of stuff. Ivermectin is a treatment that they're proposing for COVID-19.
Because of the abundant distribution of the CD147 on red blood cells, it's not going to be able to bind to the red blood cell, and it prevents, therefore, this hypothesized catch and clump framework. So catch and clump meaning the virus catches the red blood cells by 147 and then causes this clumping to occur, which may be the basis for this thrombosis. They say here, this framework whereby virally mediated bindings of red blood cells to other red blood cells, platelets, white blood cells, and capillary walls impede the blood flow, which in turn may underlie key morbidities of COVID-19.
Okay, that was one hypothesis, and this is a hypothesis proposed by these scientists here. He has proposed another hypothesis as well. So let's take a look at his hypothesis, which is in an earlier video, but we'll briefly go through it in this video as well. Let me make sure it's here. Actually, I'm going to go back and go to the other,
next month.
The other hypothesis. So let's look at the other hypothesis about blood clotting here. I think that was update 56. What happened to the list? Look at all channel videos. Well, it used to pop up right here, so that's why I didn't bother copying the link, because the one was there. I think it was 67. See, supplementary. Oh yeah, this is it here.
Build custom industrial machines.
So this is the other hypothesis about thrombosis or blood clots.
Another MedCram COVID-19 up.
Okay, let me fast forward this. Okay, here is the hypothesis. Let's watch this from here.
A tremendous job at keeping the number of new cases at bay here. Well, today we're going to go back to medical school a little bit, and we're going to talk more about our oxidative stress, because I think this is really important. And we've been building on this for the last week or so in terms of the lectures. Once again, we have oxygen. And when you take an oxygen molecule and add an electron to it, you get a superoxide. You add another electron to it, you get 2 oxygen molecules and 2 hydrogen molecules.
Well, that's not right. It's just 1 hydrogen peroxide molecule
attached to it. Another electron molecule, you get a hydroxyl, and then finally you get water. And so the most reduced form here is the H2O, or the water, and the most oxidized form here is O2. Also, please realize that when you add electrons, protons come on as well. And that's why you start to see the ratio of protons to oxygen molecules increase as you go from left to right. The body's defense mechanisms are, again, superoxide dismutase, which converts the superoxide form here into hydrogen peroxide and oxygen. There's also catalase, which converts hydrogen peroxide into oxygen and into water. And then finally, the one that we're going to talk a little bit more about is this glutathione peroxidase. And I want you to notice here that glutathione peroxidase takes glutathione, which is reduced, and it reduces the hydrogen peroxide and turns it into water, while it itself becomes oxidized into this disulfide bond, is what it's called.
So sulfur is a very common reducing agent. And so reducing agents are antioxidants, because reducing agents are the sacrificial reducing agents. So let's say, your oxidizer has a choice. It could oxidize your cells or whatever it comes into contact with and causes damage, cellular damage, or it could oxidize this, and so this is kind of the sacrificial reducing agent here, which would be an antioxidant. And so sulfur is common antioxidant. And so sulfur in this form, when we do the oxidation states, we'll see the oxidation state of sulfur in this particular compound, glutathione's -2. And then we go over here and the sulfur becomes a -1 sulfur versus -2 sulfur. So this sulfur is more electron rich over here. This sulfur is less electron rich. So this one, which is a thiol, it's an alcohol with the sulfur, which we call thiol. Thiols, remember, if you recall, thiols smell really bad. And thio means sulfur, this is like an alcohol, except it has an oxygen. So thiols are good reducing agents, This is a disulfide here, disulfide link, which is 2 sulfurs like this. In oxygen, this would be called a peroxide, but in sulfur, it's not a problem. In oxygen, when we have an oxygen link like that, it's very unstable. Here, this is a stable link, but And so this is an antioxidant. It's kind of a smelly antioxidant because thiols all kind of stink.
And so the sulfide attached to the hydrogen is the reduced form, and the sulfide attached to another sulfide is the oxidized form. That in turn.
Well, he has some issues with, it's the chemistry, because, he's calling these oxygen molecules, we call these oxygen atoms, here. And we don't call this sulfide, in that sense, because if this is sulfide, it's -2. If these are sulfides to link together, those would be -2 and -2. So he has to be more careful with the nomenclature if he's talking to a chemist, maybe to medical people. And he's a board certified. He's a professor of medicine at 2 universities, UC Riverside Medical School and Loma Linda. No, what was that? There's one other there. I forgot the name. And then he's also works in the ER, in the ICU. So he treats a lot of COVID-19 patients working in the ICU.
Turn gets regenerated back by taking the reduced form of NADP+, which is NADPH, and converting it into NADP+ through this enzyme called glutathione reductase. So there's other ways of reducing glutathione from its disulfide bond form into its sulfhydryl group. And again, the reason why this is important is because we've shown how superoxide can accumulate in oxidative stress environments, such as diabetes, hypertension, coronary disease, and that when you have COVID-19, that sets up a perfect storm of superoxide. Why is that? Once again, it's because COVID-19 hits the ACE2 enzyme, which is its receptor, and therefore there's an accumulation of angiotensin 2, which stimulates the production of superoxide. There's also a deficiency of angiotensin 1,7, which inhibits the production of superoxide through a nitric oxide mediator. In addition to this, COVID-19 itself attracts PMNs, which are neutrophils, which also can cause production of superoxide.
So ACE2 receptors are present in a lot of organs, a lot of cells, and endothelial cells, which are the cells that line the blood vessels, and many others, so in the lungs, etc. And so when COVID-19 or SARS-CoV-2 binds to that, it screws up the balance basically between angiotensin 2 and angiotensin 1,7, which causes excessive production of superoxide. Did you hear there's nitric oxide that's mediating some of these processes, NO.
And that superoxide, which is right here, is going to cause production of hydrogen peroxide and a whole bunch of other hydroxy radicals, which can cause oxidation and destruction of endothelial cells and possibly even thrombosis. So this is glutathione. And for those of you who are biochemically inclined, you'll see the backbone here of an amino acid chain, N-C-C, N-C-C. And you'll notice that this right here is the amino acid cysteine. And that's where N-acetylcysteine would come from, but it also can be regenerated, glutathione, by N-acetylcysteine, which we'll talk about in a little bit. The key point that I want you to see, however, is this SH. This is really important because this SH can also bond with another form of this molecule. And instead of having an S bound to an H, it can bind to another S. That would be the oxidized form. Here, this is in the reduced form. There's a hydrogen bounded to this sulfur group. This sulfur group can bind to another sulfur group, and that would be the oxidized form. So what does that mean?
Well, what it means is that if you've got 2 glutathiones with this SH group and you oxidize it with hydrogen peroxide, you will couple 2 of these glutathiones together in a bond that will make them connected, and you'll release water. So notice, 2 reduced glutathiones plus hydrogen peroxide gives you an oxidized glutathione plus water. And that should look familiar. Again, here we have two glutathiones being oxidized to a connected disulfide bond, and what you get is hydrogen peroxide turning into water. That's important to understand because here you have a GSH, and what you're doing is you're going to a GSS. Two independent molecules now get connected. And I'm going to plant a little seed in your head with this article, which says that disulfide bond reduction of von Willebrand factor by ADAMTS13. That's right, von Willebrand factor actually comes together and polymerizes with help, in part, with disulfide bonds. By the way, this is the same thing that happens with hair. So here is simply strands of keratin, which is a spiral structure, and a single thread of hair is basically multiple keratin fibers. And what's happened is there are S groups that are binding these together. And then what happens when you go for a perm is it's basically a reducing agent, and you break all of these disulfide bonds and you put H's on them. And then you bend the hair, so it's like this. And then what happens is you neutralize the perm agent by putting hydrogen peroxide on the perm agent. And what happens is the new disulfide bonds will form, keeping the hair with its curl. Better living through chemistry. So if in fact COVID-19 gives us an excess of superoxide and hydroxy radicals, and that excess of superoxide can in fact be taken care of through things like glutathione peroxidase, are there things that we can do to help glutathione peroxidase be in the reduced form to take care of this so we can alleviate the stress from this oxidative stress? And the answer is potentially yes. Enter N-acetylcysteine, otherwise known as NAC or NAC. As you can see, N-acetylcysteine is both an antioxidant and a disulfide breaking agent. And here's the reason why. You can see very clearly the fact that NAC has a sulfur bound to a hydrogen, meaning it's a reducing agent. And it looks very similar to cysteine, its amino acid, except it has an acetyl group bound to the nitrogen. That's why it's known as N-acetylcysteine. And as you can see here very clearly, NAC will break up these disulfide bonds and put hydrogens on them in the reduced state so that these strands will no longer be connected. So these highly cross-linked and elastic mucus gels get broken up and you get reduced viscosity. And that's exactly how NAC used to be used. It used to be inhaled for people who wanted to cough up sputum that was thick. It was a mucolytic. The other thing that NAC would do is it would take the metabolite of Tylenol. If Tylenol overdose was a concern, this metabolite from the Tylenol would be here, and it would overutilize and use up all your glutathione. Well, what N-acetyl would do is you would take off the acetyl group and you'd be left with cysteine, and cysteine would recharge glutathione and allow you to metabolize the toxic agent and prevent the cell damage and the immunoresponse that is all too well known in Tylenol overdose from liver toxicity. As you can see here, NAC acts by replenishing hepatic glutathione, which is the main endogenous nucleophilic peptide able to neutralize the major metabolite of acetaminophen, which is Tylenol. Now, in Europe, it's known as paracetamol, and it's metabolized, forming the electrophilic metabolite NAPQI, which is detoxified by glutathione. In the case of glutathione depletion, NAPQI reacts with proteins here, forming adducts, which can induce cell damage or immune response. And that's how you get liver failure and death. So you can see that NAC is a very important molecule. Not only is it favorable for saving people from Tylenol overdose, but it can also act as a mucolytic, as you can see here. But that's not all that NAC is useful for.
The article goes on to talk about how glutathione is used in many different reactions in the cell, and it can become depleted, especially in some regular type of infections like colds and tonsillitis, etc. It says here that they performed a review of the literature from 1980 to 2016 on the role of oxidative stress and glutathione play in the ear, nose, and throat conditions. The authors concluded that many ENT conditions such as rhinitis, allergic rhinitis, chronic rhinosinusitis with polyps, otitis media with effusion, chronic otitis media, and cholecystoma, tympanic membrane sclerosis, tonsillitis, Meniere's disease, laryngeal conditions, and chronic cough are associated with, you guessed it, oxidative stress and decreased glutathione, both locally in the affected tissues and systemically. Decreased glutathione levels are also associated with common features of aging, as well as a wide range of pathological conditions. So it seems safe to say here that glutathione could be recharged with N-acetylcysteine. Well, let's see if it actually works in diseases. Now, here's a study that was published in 1997 looking at a total of 262 subjects with both sexes. And this was a randomized double-blind trial looking at over 20 different centers in Italy. And they were randomized to look at either placebo or NAC tablets, 600 milligrams twice daily for 6 months. And when they looked at how many people came down with the H1N1 flu, there was no difference. Both groups came down with the same amount of flu. But when they looked at which ones actually had symptomatic forms of the flu, the placebo group, 79% of them came down with symptomatic forms of the flu, whereas only 25% of those with NAC treatment. Wow, that's an absolute risk reduction of 0.5, which means you'd only need to treat 2 people to prevent one of them from getting the flu symptoms. So they concluded that administration of N-acetylcysteine during the winter appeared to provide a significant attenuation of influenza and influenza-like episodes, especially in elderly high-risk individuals. Now, it didn't prevent the influenza infection, but it significantly reduced the incidence of clinically apparent disease. Here's another article that was published in 2010 showing that the same substance, NAC, actually inhibited viral replication and reduced these inflammatory cytokines, these pro-inflammatory molecules. And the recommendation was that, therefore, antioxidants like NAC represent a potential additional treatment option that could be considered in the case of an influenza A virus pandemic. Now, here's a meta-analysis looking at the effects of N-acetylcysteine treatment in acute respiratory distress syndrome of all types. And this was a meta-analysis, again, in 2017. Now, remember that the definition of ARDS had changed, and so the number of trials here may be a bit heterogeneous. But what they found was that there was a statistically significant difference in the length of ICU stay, even though there wasn't a difference in the 30-day mortality or the short-term mortality. And they left by saying, as the number of included trials in patients was small, additional trials are required to provide sufficient evidence for the efficacy of NAC in ARDS. But as part of their criteria and as their rationale, they do say here that removal of reactive oxygen species by antioxidants has been applied in clinical practice, and that NAC is the most commonly used antioxidant. Another key finding is that no severe adverse reactions were observed in the patients that were included. Here's another article, this one published in 2018, titled N-acetylcysteine Improves Oxidative Stress and Inflammatory Response in Patients with Community-Acquired Pneumonia. And what they did here was they looked for different levels of oxidative stress. And what they found were these levels of oxidative stress were similar between the 2 groups before treatment, but that plasma levels of MDA and tumor necrosis factor alpha decreased more in the NAC group than in the non-MAC group, including total antioxidant capacity. Again here, they said that no NAC-related adverse effects were observed. Of course, this is for community-acquired pneumonia, not COVID-19. it may be that oxidative stress plays more of a role in COVID-19 than it does in community-acquired pneumonia. In fact, it might play a great role because, as we've shown before, this oxidative stress may lead to thrombosis from hypercoagulable state from von Willebrand's factor. There may be another front that N-acetyl is opening up here with COVID-19, in that N-acetylcysteine may not only affect the oxidative stress aspect of COVID-19, but also the hypercoagulable state that is set up by the excess of von Willebrand's factor. Here we have this article that was published in 2013, which shows that N-acetylcysteine can have an effect on the coagulation factors in plasma samples from healthy subjects. They concluded that they were able to demonstrate a significant decrease in the activity of coagulation factors 2, 7, 9, and 10 with the addition of N-acetylcysteine. This would mean that the patient's blood would be thinner or less apt to clot. This paper was published in 2006 looking at the effects of N-acetylcysteine on blood coagulation and platelet function in patients undergoing open repair of abdominal aortic aneurysm. And what they concluded was that NAC has an anticoagulant and platelet inhibiting property in patients undergoing major vascular surgery. This abnormal hemostatic activity should be considered when NAC is administered to patients with increased bleeding risk. And the articles just keep coming. This one published 2 years ago. They said they previously demonstrated that diabetes exacerbates stroke-induced brain injury, and that this correlates with brain methylglyoxal to glutathione status. Again, our friend glutathione. Cerebral injury was reversed by N-acetylcysteine. Here we tested if the prothrombic phenotype seen in the systemic circulation and brain during diabetes was associated with increased Mg glycation of proteins, and if NAC could reverse this. So what they did was they gave NAC, and this is what they showed. They said collectively these results show that the diabetic blood and brain become progressively more susceptible to platelet activation and thrombosis. I would have to assume that this might be through the same process of oxidative stress. NAC, given after the establishment of diabetes, may offer protection against the risk of stroke by altering both systemic and vascular prothrombotic responses via enhancing platelet GSH and GSH-dependent Mg elimination, as well as correcting levels of antioxidants such as superoxide dismutase 1 and glutathione peroxidase 1. These are both enzymes that are specifically discussed here on our videos. And now the best paper yet. This one published just 3 years ago. Now remember what we said about oxidative stress in COVID-19. We thought that the oxidative stress was causing endothelial damage, and that endothelial damage was causing the release of von Willebrand's factors, which was cross-linking and allowing thrombosis to occur and the hypoxemia perhaps in COVID-19. Well, here's a paper titled Potent Thrombolytic Effect of N-acetylcysteine on Arterial Thrombi. Let me just say, Circulation is a very prestigious journal. Certainly it is peer-reviewed. And what they say here is that platelet cross-linking during arterial thrombosis involves von Willebrand's factor multimers. Therefore, proteolysis, that means breaking up, of von Willebrand factor appears promising to disaggregate platelet-rich thrombi and restore vessel patency in acute thrombotic disorders, such as ischemic stroke, acute coronary syndrome, or acute limb ischemia. NAC, or N-acetylcysteine, can reduce intra-chain disulfide bonds. There it is. Remember what we said? That N-acetylcysteine can actually break up these SS bonds. Well, here is a place where it might be able to help in terms of breaking up these clots. In large polymeric proteins, in the present study, we postulated that NAC might cleave the von Willebrand factor multimers inside of occlusive thrombi, thereby leading to their dissolution and arterial recanalization. That means opening up the arteries once again. So what did they find? Exactly that. NAC administration promotes lysis of arterial thrombi. These are the same kind of thrombi that might be acting in COVID-19 in the pulmonary vasculature and in other places as well. They found that the thrombolytic effects of NAC is principally at the von Willebrand factor, and that if you administered it with a GP2B3A inhibitor like integralin, which is another medication, that it actually improved its thrombolytic effect even more. That this was not accompanied by significant worsening hemorrhagic stroke outcomes, suggesting that it exerts a thrombolytic effect without significantly impairing normal hemostasis. We provide evidence that NAC is an effective and safe alternative to currently available antithrombotic agents to restore vessel patency. Fascinating. And here is another article that was actually just published earlier this year, again showing the same thing. N-acetylcysteine inhibits thrombosis in a murine model of myeloproliferative neoplasm. Here's another article published in 2011 showing that NAC reduced the size and activity of, you guessed it, von Willebrand factor in human plasma and in mice. And here you can see in the Journal of Clinical Investigation these long multimers of von Willebrand factor. And you can see in the control the number of strings versus that in NAC. So basically it cuts these things up. So you may ask, well, how come no one's talked about N-acetylcysteine before? Well, here's a review that was done last month on April 14th, titled N-acetylcysteine, a rapid review of the evidence for effectiveness in treating COVID-19. And they do go through a very nice review where they look at NAC for acute respiratory disorders. But again, this is before we really understood that maybe COVID-19 is not just a respiratory disorder, but it's maybe also a vascular disorder causing thrombosis, which is causing a lot of the hypoxemia. So they did look at NAC in terms of acute respiratory disorders. And the verdict that they came up was that clinical trial evidence for the use of NAC as an antioxidant in influenza and other acute viral respiratory tract infections is very limited and therefore difficult to draw any concrete conclusions without further trial evidence. And so they go through the data here in terms of its antioxidant properties, but they really don't touch at all on NAC and its ability to cleave those disulfide bonds and break up and thrombolyse some of these clots that we are seeing. And it's well referenced. So when I went to clinicaltrials.gov to see if anything was being done, I did find only one study, a study of N-acetylcysteine in patients with COVID-19 infection. And if you look here, they're actually giving it to patients who have severe disease, which I was very happy to see. They were trying to enroll 86 participants. It was a non-randomized trial, and it was a phase 2 study of N-acetylcysteine in severe or critically ill patients with refractory COVID-19 infection. And they're not fooling around, folks, because they're giving 6 grams a day of IV N-acetylcysteine. And they're going to give it up to 3 weeks in duration or until they're discharged from the hospital, admitted to a critical care unit, intubation, toxicity, or death. Let's take a look at our hypothesis one more time. So we got SARS-CoV-2 that comes in, binds the ACE2 receptor, thereby taking it out of action. So you have reduced ACE2. As a result of that, your angiotensin 2 increases and your angiotensin 1,7 decreases. That causes an increase in superoxide. That increase in superoxide causes oxidative stress, which causes endothelial cell dysfunction, which increases the amount of von Willebrand factor released from the subendothelial space, and that causes thrombosis. And potentially it's the thrombosis that's causing the hypoxemia and other things in the pulmonary system. So the nice thing about N-acetylcysteine is that it could act here to reduce the oxidative stress, and it can potentially act here to reduce the amount of von Willebrand's factor monomers and polymers coming together and forming these clots and the thrombosis that is associated with it. Again, we have no evidence that this would work in COVID-19 because we haven't done the trials. But if we connect the dots, it looks promising. And more importantly, in a number of studies where they gave NAC, they did not see serious adverse outcomes. So the question that I have is, if people took NAC orally as a preventative? Could this prevent serious forms of COVID-19, just like we saw with influenza A? It didn't reduce the amount of infections, but it reduced the severity of the infections. The next question is, if given in high enough doses intravenously in the hospital, can it prevent the patients from progressing to intubation and intensive care admission? If you think these videos are helpful,
Okay, I accidentally skipped the video on the von Willebrand's factor, which I'll show that to show the origin of the von Willebrand's factor from the endothelial cell damage. But the bottom line of this is NAC is an antioxidant, and NAC, you can purchase this. And so he himself takes, I think, 1,200 milligrams, 1.2 grams per day. I started taking this as well. I'm taking 1 gram or 1,000 milligrams of NAC per day. It's cheap, and it's you can just buy it. It's a supplement that they have. But if you believe in this hypothesis, then it makes sense to supplement with NAC. That's one. And then another video just came out the other day, so I'll show that too. But we'll take a break. We went too long, but I wanted to finish this video before the break. So I'm going to stop it here, and then we'll take a break for at least 15 plus. I have to run to the bank really quick, and I'll be back. Okay. So I'll stop the recording here, and then I went out of sequence. I needed to show the hypothesis with von Willebrand's factor first. I just picked the wrong video. This was the next video to show NAC. But he specifically, he takes NAC, vitamin D, and a couple of others. I can't remember, but those are the two critical ones. I think vitamin C with zinc. As he's working with COVID-19 patients all the time. Okay, I'll stop the recording.